Okay, previously we did a lab where we performed titration. That was a long time ago now. And when we did titration, we used a particularly simple definition of an acid and a base. The definition we chose for the acid was that an acid was an electrolyte, meaning when you put it in water, its ionic nature forces it with the polarity of water to be ripped apart by the polarity of water. So the acid is shred into pieces, and since its cation is a proton, when water molecules attack an acid molecule and the polarity of the water pulls it apart, you get H plus free in solution. Now, bases are also electrolytes. That means they're ionic compounds which have distinct charge separation. And in the presence of water, the original Arrhenius definition of a base was that the water's polarity pulled on the ionic lattice of the ionic compound, this time containing a polyatomic anion hydroxide. And when the hydroxide is attacked, it is pulled loose, and you get free roaming hydroxides in the solution. Now, both of these processes are physical changes. The HCl in its ionic lattice is a collection of H pluses and Cl minuses, and when I put it in water, the water just separates those H pluses and Cl minuses from each other, but it doesn't do anything to alter them, so it's not a chemical change. Same thing is true with the sodium hydroxide. It is Na plus and OH minus in the ionic lattice. When you dump it into water, the polarity of the water just pulls the Na pluses and OH minus apart, but it doesn't alter them any further. If I were to evaporate the water away, I would get HCl back and I would get NaOH back. So these are physical changes for the formation of the Arrhenius acid in water. Okay, now what we're going to do is introduce a new concept for the acid material. And this is the so-called Brunstad-Lowry acid-base definition. Brunstad and Lowry worked independent of each other and came to these same conclusions, but their works were not familiar to one another. So the idea of the Brunstad-Lowry acid is given credit to both individuals because they kind of discovered it independent of one another. But what a Brunstad-Lowry acid or base can be defined by, it's a little more general, because in the Brunstad-Lowry acid-base theory, we have hydrolysis with water. Now, what's the difference here between hydrolysis and dissociation or ionization? Hydrolysis is actual reaction of the acid molecule that you put in solution with water. So the Brunstad-Lowry theory is, if you like, showing how acids do a chemical change when you place them in water. So there's a reaction of the HCl with a water molecule forming a new species. An entirely new species is formed by this reaction, and that new species is H3O+, and it's more familiarly known as the hydronium ion. So the big difference in Brunstad-Lowry theory compared to Arrhenius theory is that Arrhenius theory is a physical change. Brunstad-Lowry demonstrates acid-base processes as chemical change. Same thing is true with the Brunstad-Lowry base. In this case, I show ammonia, NH3. Now, if you dissociate ammonia, you're not going to get hydroxides in water. The action by which ammonia is basic is it hydrolyzes or reacts with water. And what you'll notice is that the ammonia yanks a proton loose from a water molecule and forms the ammonium cation. So ammonium is formed when ammonia is placed in water, and the remainder of the water molecule which is left behind is a hydroxide, so that makes the water solution basic. Okay, so one thing that the Brunstad-Lowry theory does show is that water is intimately involved in acid-base processes. As a matter of fact, if you don't have water present, you simply can't have an acid-base process. So again, the key feature here is that Brunstad-Lowry theory is a chemical change for a reaction of the material with water, and the Arrhenius definition, or the Arrhenius idea, is that I have a physical change or just an alteration of the original molecules when they are placed in water. Turns out that the strength of hydroxide and hydronium in water solutions of any type, pretty much, is very small. It's not a very large number at all. And we don't like to write small numbers because of the fact that they have lots of zeros in them, and lots of decimal places and things of that sort. So what was done by an individual by the name of Søren Sørensen was the introduction of a scale that makes small numbers that represent the concentration of hydronium and hydroxide in solution. It makes these numbers into normal size numbers. And this is called a logarithmic scale. So what we define to measure the concentration of hydronium in solution in an acid or hydroxide in solution for a base, we use the familiar units that are known as pH units. And again, this is a logarithmic scale, and what we do to find the pH of the solution is we take negative the log of the hydronium ion molarity. So you measure the molarity of the hydronium ion in a solution, that's the moles per liter, of course, and then you take the negative log of that. The reason you take the negative log is that small numbers have negative logarithms, so the negative in front of this makes the pHs positive. Now, it turns out that you can actually have negative pHs if you have strong enough acid solutions, but generally speaking, almost always, and in particular, anything we're going to use is going to have a positive pH value. Likewise, I can define another unit, which I will call the pOH, and it measures the concentration of hydroxide in solution. So what you do there is, again, with a logarithmic scale, is you take minus the log of the molarity of hydroxide in solution, and this gives us typically a normal sized number, and we can speak about the strength of hydroxide in aqueous solution using a unit known as the pOH. Now, it turns out even pure water undergoes some degree of dissociation into ionic species. So even anytime you drink a glass of water, you're drinking a little bit of hydronium and you're drinking a little bit of hydroxide. But it's such a minuscule amount that the damage caused by ingesting acid and base in this process is negligible. So what I'm showing there is taking two water molecules and dissociating them into hydroniums and hydroxides. The reason I need two of them is I'm writing this equation with hydronium. I could also write, sometimes people do this in a shorthand notation. One H2O molecule becomes an H plus and an OH minus. But here I'm doing it a little more formally, and I'm writing two water molecules have come to equilibrium with hydronium and hydroxide. Now, there's an equilibrium constant associated, of course, with this equilibrium. And it's a heterogeneous equilibrium, which means you just write it in terms of the aqueous phase components. So it's just the product of hydronium and the product of hydroxide raised to their stoichiometric powers. That would be 1 to 1. So the equilibrium constant of this is called the Kw, and the Kw is the equilibrium concentration of hydronium raised to the first power times the equilibrium concentration of the hydroxide raised to the first power, and it turns out that that number is 1 times 10 to the minus 14. Now think about that, that's a tiny number. So what that's saying is that there's not much dissociation present in the pure water sample. Okay, remember, 1 times 10 to the minus 14 is 0.1301. that is essentially an impossible to measure number. Certainly with the technology we have, that's a number that becomes very difficult to measure with any techniques other than tricky electronic techniques that we're going to talk about later. So we can measure numbers of this kind of magnitude by using electrical impulse and the relationship between charge flowing in the solution and the current that it generates. We're going to be able to actually come to the conclusion of numbers, believe it or not, that are this tiny. Okay, so let's think a little bit about what's going on here. If at equilibrium, when water dissociates, the hydronium ion times the hydroxide ion is 1 times 10 to the minus 14. And if, as you can see in the balanced equation, the stoichiometry says that the hydronium ion at equilibrium should equal the hydroxide ion at equilibrium because they're in 1-to-1 stoichiometry. So when this comes to equilibrium, these two numbers are equal and their product is 1 times 10 to the minus 14. So the equilibrium concentration of either the hydronium or the hydroxide must be the square root of 1 times 10 to the minus 14. And I can even do that in my head. What we're saying is, in pure water, the equilibrium concentration of hydronium and hydroxide is 1 times 10 to the minus 7. Because 1 times 10 to the minus 7 times 1 times 10 to the minus 7 gives me the 1 times 10 to the minus 14. So if I wanted to write the molarity of H3O plus in pure water, or the molarity of hydroxide in pure water, I'd have to write the number 0.000001. And again, we don't like to write that number, so what do? We take the negative log of that number. And when you take the negative log of 0.000001, you get very familiar numbers. You get a pH of 7, and you get a pOH of 7. Your mom and them know, probably, that water has a pH of 7. And that is the negative log of the equilibrium concentration of hydronium ion present in a sample of pure water. Now we can take this a little further and now use these concepts to measure hydronium and hydroxide concentrations in any aqueous solution. Anytime water is the solvent, you're going to have some forms of hydrolysis with the water, and you're going to have some alteration of these hydronium and hydroxide values. When the pH is altered in a solution, that means you've created an imbalance between the H3O plus and the OH minus. But because of the idea of Le Chatelier, this equilibrium is always maintained between the two. So in any solution, whether it's acidic, whether it's basic, whether it's neutral, whether it's salt in water, whatever you want to dissolve in water, it's always true that the hydronium ion concentration raised to the first power times the hydroxide ion concentration raised to the first power is 1 times 10 to the minus 14. Any aqueous solution has this equilibrium expression expressed in it. So now what we can do is to make this into a more tractable equation with more straightforward numbers is I do a trick where I take minus the log of both sides of that equation. So I'm going to take minus the log of Kw, and I give that a fancy name. I call that pKw. And the reason I put a P in front of that is just like I put a P in front of the terms for pH and pOH. pOH is minus the log of the OH, pH is minus the log of the hydronium, so pKw is minus the log of Kw. So I will take minus the log of 1 times 10 to the minus 14. As a matter of fact, that's really easy to do. Minus the log of 1 times 10 to the minus 14 is 14. So pKw is 14. Now I will take the negative log of the opposite side of the equation also. So I'm going to take minus the log of H3O plus to the first times OH minus to the first. So an interesting property of logarithms is that the logarithm of a product is the sum of the individual logs. So minus the log of H3O plus times OH minus is equal to minus the log of H3O plus minus the log of OH minus. And since those two terms are the definitions of pH and pOH, I can simplify this crazy expression down to a nice simple form. For any aqueous solution, 25 degrees C, pH plus pOH is equal to 14. Again, this holds in any aqueous solution, anything where water is present. This holds in pure water, it holds in an acid, it holds in a base, it holds in salt in water, it holds in oxygen dissolved in water, it holds in sugar dissolved in water. Whenever you dissolve any material in water, it is always true that pH plus pOH is equal to 14. And of course, keep in mind, because this is going to be an important number for later in our discussion, that in pure water, pH is equal to 7. Now, typically, we have our choice. We can measure the pH, and from the expression 14 minus pH, we can always find the pOH. We can measure the pOH and always find the pH, because pH is equal to 14 minus pOH. It has to be true. But typically the devices we use in laboratory are known as pH meters, and they will directly measure the pH for us. So more typically than not, we are concerned with the pH of a solution compared to the pOH of a solution. And a neutral solution has a 7 pH, an acidic solution has a pH lower than 7, and a basic solution has a pH above 7. As a matter of fact, for every unit of pH you go down, the solution gets 10 times stronger in acid. For every unit in pH that you go up, a solution gets 10 times stronger in base. Okay, so a neutral solution is 10 to the minus 7 OH minus and 10 to the minus 7 H3O plus. A pH 6 solution is 1 unit less. It has an H3O plus of 10 to the minus 6. A pH 5 solution has an H3O plus of 10 to the minus 5. A pH 4 has a hydronium of 10 to the minus 4, and so forth. And as you go upward, you're increasing the hydroxide. pH 7 has 10 to the minus 7 hydroxide. pH 8 has 10 to the minus 6 hydroxide. pH 9 has 10 to the minus 5 hydroxide, and so forth. So that's how the pH scale goes with hydronium or hydroxide concentration. Every unit of pH lower gives you 10 times as much hydronium. Every unit of pH higher gives you 10 times as much hydroxide. Let's look at the first of our several different calculations of the pH of a solution today. Now, those of you that are in lecture, I'm sure the the acid and base discussion is long over, but I'm sure you spent a lot of time calculating pHs of various types of solutions, so you should have some familiarity with this. Those of you who took lecture previously or have dropped lecture, I'm sorry, I hate to tell you this, but this laboratory is all about measuring and calculating pH of solutions. So all I can tell you is there's going to be a lot of calculations involved here on out. And of course, in our upcoming assessment for the final exam, there's going to be calculations of pHs of solutions involved there. So this is just a requirement for this class, so they didn't go away in lecture, and they're not going away in laboratory either. So the first of our several calculations of the pH of solution, we will calculate the pH of a diluted strong acid solution. You will be required to do a calculation of this type for your lab report, and I wouldn't be surprised if you see something like this as well on the final exam. Okay, let's look at calculating the pH when I take 1 ml of 0.5 molar HCl and I mix it with 75 mils of distilled water. Okay, so this is first off a dilution problem. What you're going to have to do is a dilution of the 0.5 molar HCl to a weaker solution of HCl. And be very careful when you do this as you identify your values. I can choose my V1 to be 1 milliliter and my M1 to be 0.50 molar, but be careful for your V2. I'm adding 75 milliliters of distilled water, but V2 is the total volume of the sample, not just how much you added, it's the total volume. The volume started at 1 mil, I added 75 mils, so V2 that I should use in my dilution expression is 76 mils. So M2 is calculated as V1 M1 over V2. We've done calculations of that type many times over. That is 0.00656 molar. Now I'm assuming that this HCl has completely dissociated. Now I'm writing this in the form that you see below, showing complete dissociation. HCl is a strong acid, and strong acids undergo complete dissociation. We had talked about that in our previous discussions. So every bit of the 0.0056 molar HCl becomes 0.00656 molar HCl becomes 0.00656 molar hydronium. And so the pH is minus the log of the hydronium, and that is equal to minus the log of 0.00656, and that will be a pH of 2.18. So this will be a calculation that you will be doing in our laboratory today. To our second type of calculation, which you're going to have to be able to do in today's lab. This is the case when we dilute a strong base and measure the pH of that diluted strong base. Okay, now remember, a strong base, much like we had a discussion on the previous slide, strong means strong electrolyte. Being a strong electrolyte means the extent of your dissociation in aqueous phase is complete. So every bit of the KOH that I'm putting in solution exists in solution as K plus and OH minus. This is indicated in the reaction by an arrow pointing in one direction and one direction only. So when you see acid-base problems with the arrow pointing in one direction, that means they are strong acid or strong base materials, because you're assuming the extent of their dissociation is complete. So I'm going to add 1 milliliter of 0.5 molar KOH. I'm going to add that to 55 milliliters of distilled water. So again, I begin with a dilution problem. I'm taking my concentrated 0.5 molar KOH and making it into a weaker concentration. We've used the dilution formula many times this semester. V1M1 equals V2M2. For V1, I'll use 1 mil. For M1, I'll use 0.5. For V2, let's be careful. Again, V2 is the total volume of the diluted. I'm adding 1 mil to 55 mils. V2 is 56 mils, and I'm going to calculate the diluted M2. So M2 is V1 M1 over V2, and when I do that calculation, I get 0.00893. Now, because this is a strong base, I assume its dissociation is complete. So if I began with 0.00893 molar KOH, I am depositing 0.00893 molar OH minus into solution. Now, unlike the previous problem, what I will calculate, since I know the hydroxide ion concentration, I will calculate the POH. POH is minus the log of the hydroxide, and that is 2.05. Now the question asks for the pH, and also the meter will read the pH. So I have to determine the pH of this solution, and I do that using the relationship that is true for any aqueous solution, and that is that pH plus POH must equal 14. So if the POH is 2.05, then the pH must be 14 minus 2.05, and the pH of this solution is 11.95. Now remember, in a basic solution, you're going to expect the pH to be above 7. In an acidic solution, you're going to expect the pH to be below 7. So this is a calculation like you will do for solution 7 in our lab today. We will also be required to calculate the pH of a so-called weak acid solution. We previously had introduced a weak acid. What we mean by a weak acid is not that it's just got a low concentration in solution. What we mean by a weak acid is that it is a weak electrolyte. And what does it mean to be a weak electrolyte? It means that the extent of your dissociation in solution is not complete. A large portion of the molecules in a weak acid remain molecularly intact. As a matter of fact, weak acids generally, many of them, not all of them, we can't say that entirely, but a lot of them are molecular and use polar covalent bonding. So there's only slight amounts of their dissociation of their components when placed in solution. So to indicate a weak acid when you are writing a schematic chemical reaction for their behavior, we will use a notation with an equilibrium arrow, which is indicating that a certain amount of the weak acid hydrolyzes with water to form hydronium, but after enough hydronium is built up in solution, the back reaction or reverse reaction of hydronium with the anion is equally likely to reform the molecular acid. So eventually this comes to an equilibrium. And there can therefore be an equilibrium constant which we will measure to indicate how much of this is present in the solution. Now I'm writing this in this particular reaction not using hydronium. I'm just writing it as a dissociation, if you like. It looks like a physical change, but remember this physical change is not an extent complete physical change. I'm forming a product of H plus and an acetate anion from the weak acid acetic acid. So CH3COOH is our weak acid. It's acetic acid. It has a K for this dissociation, which means the product over measured at equilibrium divided by reactants measured at equilibrium. It has a K value of 1.8 times 10 to the minus 5. This is a very small number, 0.000018, which means that the numerator is a very small number when the species in the pot come to equilibrium. So there's very little H plus and CH3OO minus, and there's mostly CH3COOH at the point of this equilibrium, and that is indicated to you by the smallness of the K value. Now this is called a Ka because it's associated with an acid equilibrium constant. Okay, so what we can do is write an ICE table for this. Initially, when I throw the acetic acid in the pot, it is 1.5 molar acetic acid. And we'll assume we have none of the dissociated species of H plus or acetate anion. Technically, we actually do have 1 times 10 to the minus 7th molar H plus if it's pure water, but that's such a little number compared to 1.5 molar. Forget about it. It's way lower in order of magnitude. So essentially there's 0 molar H plus in the pure water. When we start, then there's going to be a change. This reaction is initially going to flow to the right. So the change is going to be minus X for the reactant and plus X to the stoichiometry for the products. There's a 1-to-1-to-1 ratio. So the change in loss of the acetic acid is exactly the same as the change in gain of the H plus and the change of gain in the acetate anion. So when the dust settles, when it comes to equilibrium, we add the initial and the change. So for the CH3COOH, that's 1.5 minus X. For the H plus, that's X. And for the acetate anion, that's X. So K is equal to the equilibrium concentration of the products over the reactants. And in terms of these variables, that will be X squared divided by 1.5 minus X. That is equal to the Ka, or 1.8 times 10 to the minus 5. Okay, now, technically what I should do is multiply both sides by 1.5 minus X. Then I should gather the terms together and get a quadratic and put this in the quadratic formula and then solve for, I should have a term of 1.5 minus X times X on the bottom, but I simplify that by ignoring X in the denominator of the bottom of my expression. And so if I ignore the X, because I'm assuming that since K is small, that X is small, I can simplify it to 1.8 times 10 to the minus 5 is approximately equal to X squared over 1.5. So again, I ignore the X in the denominator of the actual K expression in order to avoid solving a quadratic equation. By ignoring X in that denominator, I can, and I can assume this because the 1.8 times 10 to the minus 5 is saying that X is a little number, and I'm certainly going to claim X is small compared to 1.5. So subtracting a tiny number from 1.5 is still 1.5 in that denominator. So now I can just solve a much simpler equation. 1.8 times 10 to the minus 5 equals X squared divided by 1.5. Multiply both sides by 1.5 and get 2.7 times 10 to the minus 5 equals X squared. Take the square root of both sides and get X is equal to 0.0052. Now before we go any further, we should compare X to 1.5. Was it a valid assumption to ignore X in the denominator? And we can see that it is. If I had really subtracted that X, I would have had in that denominator 1.4948, which is, for all intents and purposes, 1.5, which makes that problem so much easier to solve by avoiding the quadratic that I should have solved. So since at equilibrium X is equal to the hydronium, or the H plus, then the pH is minus the log of the H plus. The pH of this solution, I would expect, is 2.28. Now this is a calculation like you will be doing for the lab report. It'll be similar to the kind of calculation you'll be doing for solution 8. Next type of calculation we're going to do in today's lab is calculating the pH of a solution that is altered by using a strong electrolyte containing a conjugate base of a weak acid. Now we didn't go into acid base and acid conjugate base and base conjugate acid theory. This is a concept of Brunstad-Lowry. It comes about after the hydrolysis of a base in water. We can recognize a conjugate acid that is formed as a result of that. After the hydrolysis of an acid in water, we can recognize a conjugate base that is formed in that particular process. We don't really have the time and depth to go into the ideas of acids and conjugate bases, or bases and conjugate acids. I'm sure you have done such a thing in your lecture, so I have to work under the assumption that you have some basic knowledge of conjugate bases and their behavior. So let's recognize that what we're going to do in today's lab is I'm going to take a salt, or a strong electrolyte that is an ionic compound, which has as its anion the acetate anion. An acetate anion, CH3COO-, is the conjugate base of weak acid acetic acid, CH3COOH. Now it turns out that the weaker an acid, the stronger its conjugate is as a base. And as a matter of fact, the opposite is also true. The stronger an acid, the weaker its conjugate is as a base. So like for instance, for HCl, which is a strong acid, the conjugate base of HCl is its deprotonated form. That is the chloride anion. The chloride anion is a very, very, very weak base. As a matter of fact, when you put chloride into water, it does not change or hydrolyze with the water. It doesn't affect pH. But because acetic acid is a much, much weaker acid than hydrochloric acid, its conjugate base, acetate anion, is a much, much stronger base than the chloride ion, which is the conjugate base of HCl. So what I'm going to do in today's lab is I'm going to throw some sodium acetate into water. And because sodium acetate is a strong electrolyte, it will completely dissociate as I'm indicating with an arrow pointing in one direction. The sodium acetate in solution dissociates into sodium cations and acetate anions. Now, sodium cations are the conjugate acids of strong base sodium hydroxide. So they have no acidic character when placed in water. They don't hydrolyze with water to form H2O+. However, acetate anion is the conjugate base of weak acid acetic acid. Since it is the conjugate base of weak acid acetic acid, it has a substantial basic character. So when acetate anion is delivered into water, whether it came there from whatever source, it finds water molecules and hydrolyzes with them. Why? Because when acetate is present in water, it must be in equilibrium with acetic acid. So the acetate, as the bottom reaction shows, runs around in the water, grabs water molecules, hydrolyzes with them, takes protons away from them, forms molecular acetic acid, and leaves behind hydroxide anions. It is the presence of these hydroxide anions, which are placed in water, which makes the water basic. So sodium acetate solutions have pHs greater than 7 because the acetate anion that you put into water hydrolyzes with the water, making the solution basic. Now, to find the Kb which governs this, there is a relationship that I'm sure you discussed at greater detail in lecture. We again don't have the time to discuss this as thoroughly here in laboratory, but the relationship between an acid, a weak acid and its conjugate base, or a weak base and its conjugate acid, is that the product of the Ks of those substances is equal to Kw. And remember, Kw is 1 times 10 to the minus 14. So for any acid conjugate base pair, for any base conjugate acid pair, Ka times Kb equals Kw. So since this is acetic acid, I know the Ka of acetic acid, as used on the previous slide, was 1.8 times 10 to the minus 5, so that Kb for the hydrolysis of acetate anion in any aqueous solution must be equal to Kw divided by Ka. That's 1 times 10 to the minus 14 divided by 1.8 times 10 to the minus 5. The Kb of the acetate anion, anytime it's put into solution, is 5.6 times 10 to the minus 10. Now again, that is a relatively tiny number. So I'm going to take the equation for the hydrolysis of this weak base, acetate anion, in water. It pulls a proton loose from the water, making its conjugate, which is acetic acid, and making the water basic by leaving OH minuses into the water. Since I prepared 1.25 molar sodium acetate and it completely dissociates, I have put into water 1.25 molar acetate anion. Now, when this is the initial value of it before the hydrolysis, I have no acetic acid molecules yet, and I will say I have 0 molarity of hydroxide anions present. Now again, technically, even in pure water, there is hydroxide, and in pure water, 1 times 10 to the minus 7th molar hydroxide, but compared to 1.25, 0.000001 molar is negligible. So I will assume then, without lack of precision in my calculated answer, that I can use 0 for the initial hydroxide. Now I have change. This is an equilibrium. The extent of the hydrolysis is not complete. Not every acetic acid or acetate anion, forms an acetic acid. As a matter of fact, you can tell this by the size of Kb. Kb was 5.5 times 10 to the minus 10. That's saying that the right-hand side of the equilibrium expression is tiny compared to the left-hand side. So I don't expect a large degree of hydrolysis from this because of the size of the K. So I have some amount of change that will undergo during this equilibrium process. And according to my ice formulation, since the reaction is flowing right, and since the stoichiometry is 1 to 1 to 1, then the magnitude of change is negative x for the disappearing acetate anion, plus x for the appearing acetic acid molecules, and plus x for the appearing hydroxide anions. So when the dust settles and I come to equilibrium, the equilibrium values of each of these species can be found by summing the initial value plus the change. So that'll be 1.25 minus x for the acetate anion, x for the acetic acid molecules, and x for the hydroxide. So now I write the Kb expression for this heterogeneous equilibrium. It is CH3COOH times OH minus divided by CH3COO, all measured at equilibrium. So Kb, which is 5.6 times 10 to the minus 10, should equal x squared divided by 1.25 minus x. Now again, what I should do is multiply both sides by 1.25 minus x, gather up all the terms, solve the quadratic, and get 2 values for x. Or, because k is small, I make the assumption that the product side of the reaction is small. And if the product side of the reaction is small, x is small. And x is so small that it is negligible relative to 1.25. So I will ignore x in the denominator of the equilibrium expression to simplify it so that I don't need to solve a quadratic. So 5.6 times 10 to the minus 10 is approximately equal to x squared over 1.25. I multiply both sides by 1.25. I take the square root, and I get x is equal to 2.6 times 10 to the minus 5 molar. Now, before I go on, let's verify the validity of our assumption. X I found was 0.000026, and I ignored it in the denominator by claiming x was way less than 1.25. You can see that x is way less than 1.25, so it's ignoring it in the denominator doesn't change the significance of the denominator drastically enough to affect the significance of the outcome of the x calculation. So x is equal to 2.6 times 10 to the minus 5 molar, and according to my ice table, that is equal to the hydroxide ion concentration at equilibrium. So since it's the hydroxide ion concentration at equilibrium, I can use it to calculate a pOH of the solution. pOH is equal to minus the log of 2.6 times 10 to the minus 5, and I would get for pOH 4.58. What we want to compare to is the measured pH of the solution, and And for any solution, whether it's acidic or basic or neutral or salt or sugar or whatever, pH plus pOH is equal to 14. So in this case, pH must equal 14 minus 4.58, and pH is therefore 9.42. Now you will have to do a calculation similar to this for solution 9 in your laboratory that we do today. The rest of the laboratory measurements and calculations will explore the properties of buffers. Buffers are very important biological entities. They keep us alive when we ingest acids and bases, because if you buffer an environment, an aqueous environment, buffering the aqueous environment enables that environment to resist dramatic change in pH. Living organisms, at least complicated living organisms like us, prefer to live at pHs around 7, around neutral pH. Now, believe me, there are critters out there, particularly critters that live in the stomach, critters that live around the vents of volcanoes, that love to live at pHs that have 1,000,000 times or maybe 100,000 times as much acidic content as a neutral solution. So it is possible that life can exist in pHs far away from 7, but complicated systems of life all have buffering or exist around pHs of 7. So if you ingest high pH or low pH entities into that system or deliver them into that system, you can kill these life systems. So life systems have to be buffered to prevent dramatic change in pH when acid or base is introduced. Now, a buffer can be prepared in one of two ways. It can be prepared by mixing a weak acid with a strong electrolyte containing its conjugate base, or it can be prepared by mixing a weak base with a strong electrolyte containing its conjugate acid. We will do our buffer by technique number 1. So that'll be the type of buffer we're going to be examining in today's lab, mixing a weak acid with a strong electrolyte containing its conjugate base. And as a matter of fact, this weak acid and conjugate base were the subjects that we used on the previous slides. Let's look at the form of buffer that we're going to be looking at today. Again, we're going to make a buffer by mixing the weak acid, acetic acid, with a conjugate base containing, with a strong electrolyte containing its conjugate base, and that is sodium acetate. So if I represent the weak acid as HX and the conjugate base as X minus, again, that would be CH3COOH and CH3COO minus. Those will be the two that we are using. Then I have my weak acid represented by CH3COOH, giving H plus and CH3COO minus. And then I have my sodium acetate ionizing to form NaCH3COO minus in solution. And when I combine those, the pH of this buffered solution can be derived from the so-called Henderson-Hasselbalch equation, which is pH equals pKa plus the log of the CH3COOH COO minus divided by the CH3COOH concentration. Now, I'm sure you did a much more thorough derivation of the Henderson-Hasselbalch equation in your lecture. We're just going to use the equation as here. Again, we could spend another hour talking about its development for the general form of a weak acid and its conjugate base, but this is the form in which we will use it today. Now, what is pKa? pKa is minus the log of the Ka of the weak acid, whatever that weak acid happens to be. In our case, that is, for acetic acid, 1.8 times 10 to the minus 5. So that will be the value we use. We'll take minus the log of that, and that'll be the pKa of our solution. Talk about what happens when you add water to a buffer. Let's look at it from the perspective of the Henderson-Hasselbalch equation. pH equals pKa plus the log of the CH3COO minus, measured when you start, divided by the CH3COOH when you start. Initial concentrations of the weak acid divided into its conjugate base concentrations. Well, that logarithm term will be changing when I add water. Why? Because those are molar concentrations of the conjugate base and the weak acid. So I'm going to make those concentrations lower. I'm going to be diluting the conjugate base. I'm going to be diluting the weak acid when I add water. However, the factor by which I dilute the conjugate base and the weak acid is exactly the same. Let's say I double the amount of water so that the molarity of the conjugate base is 1/2 as what it started. Well, I also doubled the amount of water when I put it into the buffer for the weak acid as well. So its concentration is 1/2 of what it started. So when you dilute the buffer, you dilute both the weak acid and its conjugate base to exactly the same extent. So that factor divides out in the ratio of molarities in the logarithm term. So there is no factor that goes into the expression because it cancels, because the same number is present in the numerator and the denominator. So adding water to the buffer does not do anything to that logarithm term, and therefore does not do anything to the pH of the solution. So the pH should be unaltered when you add water to a buffer. Now let's contrast that to what happens when you add water to just a pure strong acid solution. When I add water to it, I am diluting only the strong acid. So as its molarity goes down, adding water to a strong acid will make its pH go up because it's less concentrated strong acid. Contrastly, if I add water to a strong base, I am diluting the strong base, but that's all that I'm diluting. I'm making the concentration of it lower. When I calculate the pH, I will get a value of the pH that is less than it was originally. The stronger the base, the higher the pH. As I dilute the base, the pH will get lower. And conversely, the stronger the acid, the lower the pH. When I dilute the strong acid, I will raise the pH. So in buffers, though, because I have this cancellation of the dilution effect in the logarithm term, then the pH of the buffer is not affected by adding the water. So you should compare this to a measurement that we will make when we do the experiment at the end of the lab. Use the Henderson-Hasselbalch equation to find the pH of a solution that we make by mixing a quantity of a weak acid and its conjugate base. This will be a calculation, of course, similar to what you're going to have to do to complete today's experimental lab report. So let's just suppose I mix 40 mils of 0.2 molar acetic acid, and I mix it with 20 mils of 0.1 molar strong electrolyte, sodium acetate. And the strong electrolyte, sodium acetate, ionizes completely, making 0.1 molar sodium plus and 0.1 molar CH3COO minus, the conjugate base. So the first thing I'm going to do is recognize that the weak acid has a Ka value of 1.8 times 10 to the minus 5. That needs to be put into the Henderson-Hasselbalch equation using it as a pKa. But before we do that, let's first find the logarithmic term of the Henderson-Hasselbalch equation. I put in 40 mils of the weak acid, that's 0.0400 liters of the 0.2 mole per liter solution. I put in 0.00800 mole of the weak acid, which I'm schematically representing as HX because I was getting too lazy to write all the characters out. So that's my weak acid moles that I put into the solution. The sodium acetate, as I said, dissociates completely so that the molarity of the acetate anion is equal to the molarity of the starting sodium acetate, which was 0.1 molar. So I put 20 mils of that into the solution. So that means the number of moles of conjugate base that I put in was 0.0200 liters, or 20 milliliters, times 0.1 mole per liter, or 0.00200 mole of the X minus, which is the conjugate base. Again, I was getting too lazy to write out the CH3COO minus, so that's representing the conjugate base. So I have 0.008 mole of weak acid, I have 0.002 mole of the conjugate base. I'm now going to stick these numbers into the Henderson-Hasselbalch equation, also using the Ka is 1.8 times 10 to the minus 5. First I will find the pKa of acetic acid by taking minus the log of the Ka, and when I do that I get 4.74. Now I'll stick my numbers into the Henderson-Hasselbalch equation, pH equals pKa plus the log of the conjugate base's initial molarity divided by the weak acid's initial molarity. Now remember, molarity is moles per volume, but because these buffers are both in the same volume, I don't have to divide the moles by the liters in the top and the bottom, because the liters would cancel in the top and the bottom. So I can put, instead of just using molarity units in the Henderson-Hasselbalch equation, I can use mole units since those moles are in exactly the same volume. So what I will do is take pH equals pKa, which is 4.74, plus the log of the moles of the the conjugate base divided by the moles of the weak acid. And when I do that, I get 4.74 minus 0.6, and that is 4.14 for the pH of my buffer. A lot better than doing an ice table and using a quadratic formula or solving an algebraic expression for X. So again, notice that this will be a calculation of the type that you have to do. The laboratory we're going to do does not mix the exact proportions we saw in this example, but they happen to mix 30 mils of 0.5 molar acetic acid with 20 mils of 0.5 molar sodium acetate. You're supposed to calculate the pH of that solution using the Henderson-Hasselbalch formula for your lab report that's due. Remember, the true importance of the buffer comes about because it has an incredible ability to resist the change in pH which occurs when acid or base are added to it. Now, when you add acid to a buffer, the pH will go up slightly. When you add base to a buffer, let's scratch that, let's reverse that idea. When you add acid to a buffer, pH will go down, but it will only go down slightly instead of go down dramatically, several pH units. When you add base to a buffer, the pH will go up because it becomes more basic. However, if you add base to pure water, the pH will go up by several units of pH. When you add base to a buffer, it goes up by only fractions of a unit of pH. So it can resist the change when you add these quantities into a buffered solution. So let's examine that by taking a 0.7, let's take 3/4 of a milliliter, 0.75 milliliter of 1 molar strong acid, HCl, and add that to my acetic acid sodium acetate buffer, which I made on the previous slide. Okay, so I'm going to use the moles. I'm dumping this HCl into the original buffer. This is much like you will do in the experiment. You'll take your original buffer and you will dump some strong acid into it. Now, of course, the strong acid is completely dissociated. So whatever moles of strong acid I put into the solution is equal to the moles of H plus that I'm putting into the solution. So I put 75 milliliters, which is 0.00075 liters of a 1 mole per liter solution. So I've added 0.00075 moles of H plus. Now, what does this H plus do when I put it into the solution, it creates a titration. The H plus is an acid. It reacts with the base that is present in the solution. That base is acetate anion. And when you do the titration of the H plus the conjugate base, you will form more weak acid. So adding H plus will begin to deplete the conjugate base, which was present in the acid, and will begin to increase the concentration of the acetic acid that was in the solution. So what I will start with are the moles of each that are present at the beginning. I just found out there is 0.00075 moles of H plus. From the previous problem, we learned there was 0.0020 moles of the conjugate base. There was 0.008 moles of the weak acid. So this little reaction runs to completion. The limiting reagent is the strong acid that I added. So it's H plus from that strong acid will react completely with the conjugate base that is present in the acid. And while it's doing that, it'll form more weak acid. So I run the reaction until all 0.00075 moles of H plus are depleted. There's no moles of H plus left. There is now a decrease in the conjugate base because it reacted 1-to-1 with the H plus. Now there's only 0.00125 moles of conjugate base present instead of the 0.002 moles. And I've added to the weak acid a factor of 0.00075 moles. So now instead of 0.008 moles of it, there's 0.00875 moles of it. Now with these values, I go back to the Henderson-Hasselbalch formula. pH is pKa plus the log of the conjugate base divided by the weak acid. Well, now I have new values. The pKa is still the same, but I have new values for the conjugate base moles, a new value for the weak acid moles. So now the pH of the solution has changed, and you will note it has gone down from the pH on the previous slide, but it has only gone down slightly compared to what it would go down if I dump this strong acid into pure water. Now you're going to have to do a calculation like this on solution number 2 in the lab report. This time, let's add base to our original buffer. Now notice I'm going back to the original buffer, the one I prepared a few slides back. I'm going to use the proportions of weak acid and its conjugate base that I determined from the original problem a couple slides back. This is similar to what you're going to be doing as a calculation for the lab today. So let's suppose I add 4.5 mils of 1 molar NaOH to the original buffer. Now, of course, the NaOH is a strong base, meaning it dissociates completely. So whatever number of moles of strong base were present will be equal to the number of moles of hydroxide I'm adding to the buffer. So the 4.5 mils is equivalent to 0.00045 liters times the 1 mole per liter. I'm adding 0.00400 moles of, say that again, 0.0045 moles of hydroxide into the buffer. So again, I'm now going to do a titration reaction where this base I'm adding will react with components in the buffer and change their concentrations. It's just like a titration. The base I'm adding will react with acid. And when it reacts with acid, it'll form more conjugate base. So notice the OH minus takes a proton from the H and makes CH3, takes a proton from the CH3COOH and leaves behind CH3COO minus. So remember, from the Brunstad-Lowry idea, bases are proton acceptors. So the base on the left accepts a proton from the acid on the left, leaving behind the conjugate base the deprotonated form of that acid, and the conjugate acid, which is the protonated original base. So the conjugate base of this process is what results from the OH stealing a proton from a weak acid molecule. So again, I take the moles of OH I just calculated above, and I use the original moles from the buffer solution I prepared a few slides back, and I run this as a limiting reagent where the OH minus is the limiting reagent in that reaction because it has the least number of moles present. So what will happen is that it will begin to deplete the weak acid as it reacts with it and steals protons from it. It'll form more conjugate base in the form of CH3COO minus as a result. So I will lose 0.0045 moles of the weak acid. I will gain 0.0045 moles of the conjugate base from the starting values. So when the dust settles, there's 0.0035 moles of weak acid left, and there are 0.0065 moles of conjugate base built up into the solution. So now I turn to my Henderson-Hasselbalch equation using these new numbers. The pKa is still the same as it was originally, 4.74, but now I have new values of the conjugate base and the weak acid. So I get a pH value of 5.01, which is higher than the pH of the original buffer. Now it is higher, but not substantially higher, not near as high as if I would have added 4.5 mils of 1 molar base into pure water. That would go up 5 or 6 pH units. This has only gone up a fraction of a pH unit. Now you're going to have to do a calculation like this on solution 3 in our lab report that we're going to be doing this week. Okay, so let's just look at what I did when I did the lab for you this week. I got the chemicals out. I poured them into a small beaker, and I poured each of them, not large amounts, it really doesn't matter for many of them, but you will see on the subsequent slide, I give explicit amounts for the ones that are necessary. In particular, solution number 1, 2, and 3, I state explicitly how much of each of the solutions, how many milliliters of each I'm adding, because you're going to need those in the calculations. So what I'm doing first is preparing small beakers full of the various solutions for which I'm going to measure the pH of those solutions. Then what I did was got out a pH meter, which is very, very similar to the conductivity meter, which we used in our first lab. And remember what a conductivity meter does is it measures how much current will flow through a solution containing electrolytes. Acids and bases are electrolyte solutions. They are charged species floating around in water. So if you put current into them, that current can flow, and you can measure the strength of that current. So all a pH meter does is it measures how well the solution conducts, and from the current that is flowing, the more H plus or OH minus that is present, the bigger the current, and then through the wizardry of the computer, this can be converted directly into a pH of the solution. So I take my 9 little beakers of various solutions and I stick them into the I stick the electrode down into it and hit the go button on the program, and it flashes out for me the pH of those solutions. I will show you those on the next slide. So the solutions on pages 89 and 90 of the lab manual in the Buffers lab were prepared in beakers, and then just simply the electrode was lowered down into solution, and I measured the pH of those 9 solutions. What you see on the table below are these 9 solutions, and a description of what is exactly placed into them. And you will need certainly those numbers that you see in there in the description when you do the calculated values. So I've measured these pHs. That didn't take much time at all. But what the fun is going to be for you is to calculate the pH of these as well, so you can compare them to what was measured. So you should pay particular attention to the description, because when you're going to do the calculation for each of these solutions, you're going to need to know the volume of various components I put in, and also equally important, the molarity of each of these components that I put in while I was doing and preparing those solutions. So let's talk specifics about the lab report. It should be uploaded to the lab report Dropbox for this experiment by Friday, May the 1st. That will be after our final exam. Our final exam will be next week, or it'll be that same week, but Friday, the end of that week, will be when this lab report is due. I would tell you, though, that you should not hesitate to look at these calculations, because, of course, many of these calculations are going to be components of the final exam that will be given out earlier in the week before this is due. So again, you shouldn't wait to look at these things. You should do them in a prompt fashion so that you'll understand how to do some of these things for the final exam. So what should go into this lab report? First, it should have a title page with the experiment number and name and your name. Then it should have a table with 9 rows, and it should be very similar to the little table I showed you before, but you don't really have to put the description of the solutions, but you should number the rows 1 through 9. You should put the experimental pH, which is given on the previous slide. Then you should put the calculated pH. Now, of course, remember, I know what these calculated pHs should come out to be based on the components and the amounts and strengths of solutions that are used on the slide you see immediately before this slide. You should calculate the pH based on that amount of each material put into the beaker, and you should compare it to the experimental value. Now, there are examples of how to do each and every one of these calculations on slides prior to this slide, and remember, you're going to be responsible for being able to do calculations of these types when we have our final exam at the end of the week, earlier in the week prior to when this lab report is actually due.